Okay, we want to find the absolute maximum and minimum values of the function f over this region. Okay, first thing I'm going to do is draw a picture of that region. Okay, we have that x is between 0 and 15. We have that y is between 0 and 15 minus x. So if you graph the line y equal 15 minus x, it's going to be that line. Okay, and this is the x-axis, where x is 0. Okay, so what we want to do, if we're trying to find absolute max and mins, the first thing we do is we look at critical points. So you find critical points, then you find points on the boundary where they're going to have the highest and lowest values for the function f, and then you just check all those points, the critical points and any of the ones on the boundary, and see which one gives you the largest f value. So we'll keep a running track of those as we find them. So the first thing we want to do is find critical points. And you do that by finding the derivative, the two partial derivatives. The partial of f with respect to x will be y minus 8. The partial of f with respect to y will be x minus 2y plus 12. Okay, critical points where each of these is 0. So this first one tells me that y has to be 8, and the second one tells me that the x has to be 2y minus 12, and since y has to be 8 for both of those to be true, x comes out to be 4. So 4, 8 is a critical point. Okay, so I'm just going to look at that point right here, 4, 8. Okay, next thing we want to do is look at the boundaries. Okay, to get absolute maximum and minimums, you always have to look at boundaries as well as critical points on the inside. So the boundaries of this region are made up of 3 segments. So I'm going to look at the 3 segments. Let's look at this segment first. Those are all points where the y value is 0 and the x goes from 0 to 15. Okay, so what I want to find is what does this function's values look like for those points? And so I can do that by, we don't have a specific x. The x is any value from 0 to 15, but we know all those points have a y of 0. So this function f of xy, then, I'm going to come up with another function that'll have just one variable that we'll be able to actually find its maximums and minimums for using our Cal1. So g of x, because only x matters here, y is going to be 0, and all I'm going to do is plug it y equals 0 into every y value up here. So I'm going to have negative 8x plus 160. This has the same values as the function f does for the points that are on this line segment where y is 0 and x is between 0 and 15. So if I want to find critical points, I can take the derivative and set it to 0. But of course that can't be 0, so there are no critical points. So that means that the maximum and minimum have to occur at the boundaries, the endpoints. So that the endpoints for x would be x equals 0 and x equals 15. And both of these have a y of 0, so I'm going to add those for that line segment. They're going to be the points 0, 0, x is 0, y is 0, and x is 15, y is 0. So these are on this line segment. So I'll just keep them colored red. Okay, now let's look at another segment, and we'll figure out what the f of x, y's are for all those points. Okay, now the next one I want to look at is the points along this border. So those points have the condition that y is 15 minus x. So now again, I'm going to go back to my f of x, y up here, and I'm going to change the y to 15 minus x. And I'm going to call that new function h. H of x will be Okay, so now when you simplify that, this simplifies down to minus 2x squared plus 25x plus 115. Okay, so that's the function that has the values of the function f of xy for points. We're just looking at points in the domain that are on this line y equal 15 minus x. So looking at these points here, it's going up and figuring out which points up here correspond to that. Okay? So I want to find the derivative, which is negative 4x plus 25. Set it equal to 0. That means that x is 25 fourths, which is 6 1/4. Okay, so that's the only critical point. So we'll do 6.25. That's a critical point for the points that are on that border. So that might be this high point up here. I need to figure out what the y value is for that x. So if I use x equals 6.25, I get that 15 minus 6.25 is 8.75. Okay, and now let's look at the endpoints of this. We're looking at this segment here, and we know that in between on that line segment that this is a critical point, 6.25, 8.75, but let's look at the points on the ends also. That would be 15, 0, which of course we already have from one of the others, and then 0, let's see, if x is 0, y is 15, so that would be 0, 15. So that's using this point up here. Okay, so I wouldn't have to do this other one twice. But those are the 3 points that I would need to check for this portion of the graph, the part in green. Okay, so now let's look at the last border. Last boundaries occur here. So those have the property that the x is 0 for all those points, and then the y is between 0 and 15. Okay, so I'm going to keep y as the variable. So I'm going to define a function k of y, putting x equal to 0 into this function f. So letting x equal to 0, we're going to have minus y squared plus 12y plus 160. So that represents all of the z values, the functions of the values of f of xy for the points that are on that black line segment. Okay, so let's find if there's any critical points. So now we're looking at, looks like we're looking at these points now. And these are the ones we looked at first. Okay, so critical point, take the derivative and set it to 0. So this is going to tell me if there's anything in the middle of that line segment where there might be a high or low value. So minus 2y plus 12. So y equals 6. I need to consider that one. And remember, the x is 0. So the y is 6 when x is 0. Okay, and then now let's look at the endpoints. The endpoints there that we'd have to consider would be 0, 15, and 0, 0, which of course are already included since they're endpoints of the others as well. Okay, so now once we get the points that we need to consider, all the critical points inside of the region, talking about inside here, that was what we set the 2 partials to 0, and then looking at each border and getting critical points for those and the endpoints. This is all the points that there might be the highest and lowest value at. So checking the f of xy for each one of these, all we're doing is taking each one of these points and plugging it into this equation. So f of 4, 8 becomes 192. F of 0, 0 is 160. F of 15, 0 is 40. F of 6.25, 8.75. is 193.125. I just do it like this. Okay, we've already done f of 15, 0. F of 0, 15 is 115. And you can just go back and check it. It's taking some time. F of 0, 6 is 196. And we've already done this one, and we've already done this one. So now, choose the absolute maximum z value, which is the value of f. So the absolute maximum would be the 196. So that is the maximum value, and it occurs when x is 0 and y is 6. So that occurs somewhere in here. Looks like it's probably right up there. And then the absolute minimum looks like it's at 40. And that occurs at when x is 15 and y is 0. So that occurs here, which would be down here. Okay, now keep in mind that surface is defined for all xy in the xy plane, but we're only looking at the piece of it above this triangle. And so the pieces, the little graph that they're showing you is just the pieces of the graph for these points. So here's the lowest point, and that's the one that occurs here at 15, 0. And then we have our highest point that occurred over at 6, at 0, 6. Let's see, x was 0 when y was 6. Yeah, x is 0 and y was 6, so it's over here. So that corresponds to that point. Okay, so if you've got absolute maximum minimum values that you're looking for, you have to look at endpoints unless the curve just keeps going on forever in every direction. So critical points and then endpoints.